Hey everybody, my name is Mikhail Shalaginov and I'm going to talk about what I have done during this summer school under the supervision of Professor Reshak. In other words, about modeling hydrogen storage materials. Let us start with the global problems of the world. And here you can see the top 10 list of the most important problems that humanity should solve in the nearest future. And the problem number one is energy. I have a question. Why is energy the problem number one? Well, the evolution of energy consumption can help us to clarify its importance. In recent years, there is a tremendous increase in energy consumption. And more than 80% of all the energy is taken from fossil fuels, like crude oil, coal, and natural gas. These are fossil fuels, and they are not renewable. And one day, they will be exhausted. And moreover, they cause increase in CO2 concentration in the atmosphere. This is probably the main reason of rising temperature, global warming, changes in climate. And this is the consequence. If we want to survive, we should find renewable and eco-friendly source of energy. So, how can the energy problem be solved? One of the most solutions is the following. The water can be heated and it splits into hydrogen and oxygen. The hydrogen can be used as a fuel, where the end product is water. At the beginning we have water, and at the end too. We have a cycle. This is the renewable and eco-friendly source of energy. This is not just an idea. This is a reality. And it is already used in car engines, plane engines, and also in power stations. But there are still some problems. And one of them is hydrogen storage. For a 200-kilometer trip, you need 2 kilograms of hydrogen. Yeah, okay. But you need a very enormous tank like this, because in normal conditions, 2 kilograms of hydrogen has volume 25,000 liters. It's enormous. You can compress it or liquidize in order to make the volume smaller, but you need extremely low temperature or extremely high pressure. These conditions are not widely used in our everyday life. So we need another storage materials maybe. And this is the solution. So one can store hydrogen in solid-state materials like metal hydrides, carbon-based materials, or complex hydrides. We are working in theoretical physics in order to predict fundamental properties of solid-state compounds. In calculations, we use very high accuracy method based on density functional theory. And now I want to concentrate on one of these solid-state materials which is suitable for hydrogen storage. So why are we concentrating on this compound? Because it has light weight, it has high capacity of hydrogen, and it is low cost. Now let me show you the results of our work. First of all, this is structure. The ground state lattice parameter corresponding to the minimum of energy was calculated by two different approximations. And one gives the result that is very close to the experimental one. Let us pass to electron band structure. Band structure is values of energy that the electron is forbidden or allowed to have. And here you can see the valence band maximum is located at the X point of the brilliant zone, and the conduction band minimum is located at the R point of the brilliant zone, resulting in indirect wide band gap. This is very important for us, because usually wide band gap materials have very strong bonds. So it means that they're very stable to external stress. Then, total density of states. Density of states is number of electron states per unit volume, per unit energy, and here you can see that it is in a good agreement with the band structure. And here is wide band gap. And the main contribution to the electron states near the Fermi level is made by potassium and hydrogen atoms. From partial density of state, one can conclude that d orbitals of potassium and s orbital of hydrogen contribute more than others. So the size of this wide band gap is controlled by these orbitals. At the end, I want to talk about electron charge density. Roughly speaking, it is the distribution of charge in space, and we're considering three different cross sections: 1, 0, 0, 2, 0, 0, and 1, 1, 0. First of all, 1, 0, 0. And here you can see that there is no charge contour around potassium and hydrogen. It means that the bonding is formed by ionic interaction. So the name of this bonding is ionic bonding. Next one, plane 200, and you can see here is a contour around the magnesium and hydrogen atoms. It means that they are sharing electrons, and this bonding is covalent. And finally, 110 plane, and here are represented all kinds of atoms: potassium, hydrogen, and magnesium. And we can conclude that potassium and magnesium are bonded with each other by hydrogen. In conclusion, the investigated material has very wide band gap that is controlled by d orbitals of potassium and s orbitals of hydrogen. And usually the materials with the wide band gap have very strong bonds. So, our material, apart from having light weight and high capacity of hydrogen, and being also low cost, is very stable to external stress. That is what we're looking for in hydrogen storage materials. This work has been formulated as an article, which will be submitted to the journal PCCP under the title Potential Hydrogen Storage Material Using Density Functional Theory. And I want to say thank you to the guys with whom I was working all this time, especially to Professor Ali Reshak, to PhD student Saeed, and of course to organizers of Schola Ludus, in order to give me a chance to participate in this wonderful summer school. So, thank you for your attention.